Hello, my name is Tom Irvine, and I'm the instructor for this series of shock and vibration webinars. And I again thank Dr. Curtis Larson and the NASA Engineering and Safety Center, NESC, for supporting this series of webinars. Today we're on Unit 29, and this is the stress-velocity relationship for shock and vibration. And the purpose of the presentation today is to give an overview of the velocity-stress relationship metric for structural dynamics. And if you remember back to your high school physics, you learned that for a rigid body in translation, the kinetic energy was equal to 1/2 mass times velocity squared. So we can say that kinetic energy is directly proportional to velocity squared. So velocity then is proposed as being the best metric for characterizing the energy stored in the modes of a vibrating system. Now when we talk about velocity for the case of base excitation, we're really talking about relative velocity. And sometimes we'll say pseudo velocity, which is roughly equivalent to the relative velocity. We use those terms kind of interchangeably. And the pseudo velocity then is a measure of the stored peak energy in the system at a particular frequency, typically one of the natural frequencies, and thus has a direct relationship to the survival or failure of that system. And this unit builds upon the work of Hunt, Crandall, Eubanks, Juski, Chalmers, Gabrus, Bateman, and others, but most particularly Gabrus, who was the champion of this method. So here's Dr. Howard Gabrus, and he passed away in 2013, and I had the privilege of being with him on 2 different occasions. And he was a shock and vibration specialist with more than 45 years of dynamic experience, and he was with the U.S. Navy Civil Engineering Laboratory and then later with the Facilities Engineering Service Center from 1968 to 2000, mostly conducting dynamics research. And Gabrus specialized in shock and vibration signal analysis and published more than 100 papers and articles. And many of these papers concern the pseudo velocity and how that's, according to his claims, and they're very good claims, that pseudo velocity is the best metric for representing shock response spectrum. And then he also wrote papers on the stress-velocity relationship. So here's some of the seminal references. F.V. Hunt wrote Stress and Strain Limits on the Attainable Velocity in Mechanical Systems, as published in the Journal of the Acoustic Society of America in 1960. S. Crandall wrote Relation Between Stress and Velocity in Resonant Vibration, also published in the Journal of Acoustic Society of America, and that was in 1962. And Gabrus and Chalmers wrote a paper called Modal Velocity is a Criterion of Shock Severity, and that was published in the Shock and Vibration Bulletin by the Naval Research Lab in December of 1969. Then also there's a textbook written by Clow and Penzian called Dynamics of Structures. So there's some obviously additional references as well, but if you like to do your own research and go back and read some of the original papers or the leading papers on this topic, then I encourage you to look up those references. So here's an infant rod, and it's vibrating longitudinally. So we're gonna consider the longitudinal stress velocity for a traveling wave along this infant rod. So there are various zones where you see the kind of dark gray that turns into black. That's where compression is taking place. And then the lighter areas that are almost turning into white, but not quite. They're just, I should say the light gray, that's refraction, where the particles are being spread apart. And then in this case, the direction of travel is from left to right. And there's a well-known relationship between the stress and the velocity for this case. So sigma is the normal stress, and it's a function of both space and time. And that's equal to minus rho c times the velocity at a given space and time. So this rho is the mass density, and c is the speed of sound in the material, and then v, the velocity, that's a particle velocity at a given point and also at a given time. And one of the reasons that this relationship is so attractive is that the frequency is not explicitly part of that equation. But of course, if we were to analytically calculate the velocity, then yes, we would need to calculate the frequency. Or another way is if we were setting up an experiment, we could experimentally measure velocity. But this simple stress velocity relationship becomes the basis of everything we're going to do from here on out. So here's another case. Again, we have a longitudinal rod, but in this case it's a finite length with fixed boundaries on both the left and right. So the waveform is traveling and then being reflected and then being reflected again, and potentially those reflections could set up into a standing wave. And for this case, we have a similar equation to what we've seen before, but slightly modified. In this case, we have sigma sub n. So this is the modal stress. Now just for simplicity, let's assume that only the fundamental mode is being excited and that all the stress is in that fundamental mode response. And when I say excited, we could have the case of zero damping, where, in other words, an undamped system where there was an initial velocity and initial displacement that set up a resulting waveform at the natural frequency. Or we could have some sort of applied force, even base excitation, driving the system into resonance. So that normal stress, it is a normal stress, and sub n actually is referring to the mode number rather than normal. The maximum modal stress is equal to rho c times the modal velocity maximum. And one kind of curious relationship or feature or idiosyncrasy, I should say, that's going to come about, especially as we get to beams and plates and other structures, is that the peak velocity and the peak normal stress do not necessarily occur at the same point. For some structures and with some boundary conditions, the peak stress and peak velocity will be at separate points. So that's kind of a little interesting thing, and we're actually going to do an example with a cantilever beam where we see that. Okay, and I think I've covered all the bullets. Let's just review bullet 3. We're going to assume the stress is due to first mode response only. Now, later on, we'll consider the case of multi-degree of freedom response. Okay, so here we have a beam bending, and let's think about the stress-velocity relationship for beam bending. In this case, the maximum bending stress is equal to c hat. Now, c hat is the distance to the neutral axis. Then we have the square root of the elastic modulus, E. A is the cross-section area, rho is the mass per volume, and I is the area moment of inertia. So effectively, these terms together equal a constant, and that constant depends on geometry and material properties. So the maximum bending stress then is equal to this composite constant times the maximum modal velocity. And again, the maximum stress and maximum modal velocity may occur at different points. And for right now, we're still kind of just being simple and assuming that the stress is due to the first mode only. So in other words, the response of the beam, even though it's a continuous system, is just in its first mode, its first bending mode. And this formula will work for a variety of different excitation sources, including initial conditions like initial displacement, initial velocity, or applied force or base excitation. Plates are more complicated, and actually in an upcoming unit we're going to go over a kind of a simplified way of analyzing the plate bending stress-velocity relationship. But going back to the seminal 1960 paper by Hunt, he wrote, "It is relatively more difficult to establish equally general relationships between antinodal velocity and extensional strain for a thin plate vibrating transversely, owing to the more complex boundary conditions and the Poisson coupling between the principal stresses. But he did come up with a formula for higher modes for an intermodal segment. So imagine there are a series of nodal lines sort of crisscrossing this rectangular plate, and he came up with a formula where, okay, for some higher mode where there's just sort of a patch here in between these nodal lines, we can come up for a formula for the stress and velocity relationship for that patch. And we'll maybe talk about that more later, but actually we're gonna use a simpler method. But I just wanted to mention this because this is in the in Hunt's 1960 paper. So we can kind of just sort of generalize this into a formula here where we have the maximum stress for modes, and the sub-n refers to the mode number, is equal to K. Now K is a constant proportionality. We'll talk about that here shortly. Rho C. Now, oh, by the way, the rho C I think has some other names. I think it's sometimes called the specific impedance or the acoustic impedance. And you can fact check me on that. And then we have the maximum modal velocity V sub n. So this K factor here, now let's consider we have some complex structure. It could be an assembly of plates and beams or cylindrical shells, whatever. And this K value here, this constant proportionality, which depends on geometry, according to Bateman, it could vary from 4 to 8. And Gabrus was more conservative, and he said, well, that K value can vary from 1 to 10. And I have a note to self, to-do list, come up with case histories for further investigation and verification. Or if anyone else needs a project, you can go ahead and go with that and see what you come up with. We've talked about Mill Standard 810E before. Now, okay, I realize that Mill Standard 810 has been revised to Rev F and G, or I think H is in the works. But anyways, going back to Mill Standard 810E, there was an empirical rule of thumb stating that a shock response spectrum is considered severe only if one of its components exceeds the level, and then here's the threshold, the not to exceed threshold, 0.8 G per hertz times natural frequency in hertz. This formula should look familiar to you. We've actually covered it before when we were talking about shock response spectrum, and now it's time to revisit that rule of thumb and to build upon it. So let's say, for example, we had 100 hertz natural frequency. That was the natural frequency of our component. The severity threshold would be 80 Gs. And this rule is effectively a velocity criterion, and the Mill Standard Rev E stated that it is based on unpublished observations that military quality equipment does not tend to exhibit shock failures below a shock response spectrum velocity of 100 inches per second. Well, if you actually work through the mathematics of that formula in the bullet 2, that actually corresponds to 50 inches per second. So there's a built-in 6 dB margin of conservatism. And this rule was not included in Rev F or G, but I have seen it referred to in some other references that I'll refer you to later on. So this is a good rule of thumb for military quality equipment. Now, if you have a component that's, say, a commercial grade or is just some extra sensitive component, then you want to be more conservative than what that threshold rule indicates. But if it is military quality equipment, sometimes that formula in bullet 2, this one here, could be used to decide whether or not shock testing was even required. And another, probably a little better way than using that rule of thumb, or maybe I should say just a supplementary way, is to see whether maybe the random vibration environment is high enough to cover your SRS shock requirement. And we'll we'll talk about how to do that in an upcoming webinar. Okay, so here is a V-band bolt cutter shock. This is measured data from a ground test, measured near the source. We have acceleration in G versus time in seconds. Now, as we look at this data, well, first of all, let me back up. When I say V-band, this is like a clamp band, or sometimes it's called a Marmon clamp, and it might have 2 or 3 segments joined together to form a hoop. So imagine that you have to take 2 cylinders and connect them together. Like these could be modules in a launch vehicle, and there's a joint between those 2 cylinders, and the V-band sort of clamps that joint down so that the 2 cylinders are fastened one to another. And this would be like in a launch vehicle. So then during the portion of flight, when it's time to separate the 2 modules one from another, then there might be, say, some cartridges. Now these are cartridges that have a little pyrotechnic charge inside, and the charge is set off, and the charges drive a guillotine blade, and the guillotine blade cuts the bolt that connects the clamps together. And when I say that, there could be several bolts at a given azimuth or clocking angle, as well as between other segments as well. So there could be 2 or 3 or 4 bolts, whatever, cut in order to have the V-band release. Now, some of the pyrotechnic shock originates because there is a pyrotechnic little explosive charge in these little cartridges, and that does create some pyrotechnic shock energy that propagates as mechanical shock. But probably an even greater source is that these V-bands or clamp bands, their connecting bolts are torqued down, and that creates a lot of strain energy in these clamp bands. And the sudden release of that strain energy definitely contributes to the overall shock. So here you're seeing a measured data, and this is getting up to about 230 Gs maybe. So the question is this severe? Is this something that we need to be concerned about? If we have any nearby mounted components, do those components need to undergo a special qualification shock test? Maybe do they need to be mounted via isolators? And those are good questions to ask. So let's go ahead and we're going to look at the pseudo velocity. And just as a review, if we have the absolute acceleration A, then we have a pseudo velocity PV. C will be the relative displacement, and omega sub n will be the natural frequency in radians per second. Well, a pseudo velocity is approximately equal to the acceleration divided by omega sub n. That's one way to calculate pseudo velocity. And another way to calculate pseudo velocity, which is actually the preferred way, is to say pseudo velocity is approximately equal to omega sub n, which is the natural frequency in radians per second, times the relative displacement. Now pseudo velocity is it's sort of a slightly fuzzy term. So when we say pseudo velocity, it's sort of the approximate relative velocity. But let's just remember, when we use pseudo velocity, we're engineers. We're not physicists. So let's go back to that V-band acceleration time history. So this was a separation event, the ground test. There's actually a shroud separation. And along the y-axis, we have velocity in seconds. Along the x-axis, natural frequency in hertz. And this is SRS, Q is equal to 10. And I'm presenting this in what Gabrus would call the 4-coordinate plot. Or I tend to call it a tripartite plot. Either way is fine. And if we look at this point here, that we can see, oh yeah, the SRS gets up to about maybe about 1100 Gs at about, let's see, 987, about 6,000 hertz. So that's the peak acceleration on the SRS. But let's look at the peak velocity. Well, the peak velocity is within about 12 inches per second. And 12 inches per second is well below the conservative 50 inch per second threshold via that empirical formula that we took a look at earlier. So this V-band bolt cutter shock is really not so severe after all. Having said that, though, when in doubt, test. And another thing sort of to look at is that certainly the velocity, the pseudo velocity, it varies with natural frequency, that's clear. But the dynamic range, so if I say dynamic range, that's the ratio between the maximum peak and then the minimum level. So we could call that the dynamic range and maybe represent that in terms of dB. But in many cases, certainly not in all cases, but in many cases, the dynamic range of the pseudo velocity is less than the dynamic range of acceleration. So if we look at acceleration for this acceleration time history, it takes about 3 or 4 decades to represent the acceleration SRS. And if we turn our heads 45 degrees counterclockwise, we'll see that it also takes 3 or 4 decades to represent the relative displacement. But velocity, while certainly not constant with natural frequency, is more stable with natural frequency than either relative displacement or absolute acceleration. And that's another feature that makes the pseudo velocity an attractive metric for characterizing the damage potential of shock. Okay, here's something else. This is a Space Shuttle solid rocket booster, and of course the Space Shuttle had 2 of these boosters per launch, and the boosters were at a certain point in flight were separated and jettisoned, and then parachutes deployed so that these boosters could be recovered out in the ocean, and they were shipped back to shore and were refurbished and flown again. So the parachutes helped mitigate the water impact shock. And it turns out that within these solid rocket boosters there were some avionics components. And those avionics components were likewise recovered and refurbished and retested and all that, and then they were flown again. So we have some actual data, and this is from a Space Shuttle solid rocket booster water impact. So there were 2 IEA boxes. These were large avionics boxes, one mounted in the forward end and the other in the aft end of each booster. So you have acceleration in G and time in seconds. And this is data from the STS-6 mission, if you're a Space Shuttle fan. And actually I have a little note, some high frequency noise was filtered from the data. So just let me back up a little bit. When these solid rocket boosters were undergoing their water impact, there was obviously a variety of variables that would affect that shock. The wind, the sea state, the wave height, the angle at which that booster struck the surface of the ocean. Those were all variables. So here again is that acceleration time history for an SRB water impact. And so we see that this peak here is getting almost up to about 90 Gs. So the question is that severe or not? Yes or no? So here we have a 4-coordinate plot or tripartite SRS, Q is equal to 10, for the SRB water impact as measured near the forward IEA location. So we have velocity in inches per second and natural frequency in hertz. And we can see that the peak pseudo velocity is just a little bit over 200 inches per second. So according to that Mill Standard 810E rule, and depending on whether we're considering 50 inches per second or 100 inches per second to be the threshold, well, for the case of 100 inches per second threshold, we're about 6 dB higher, and for the case of a 50 inches per second threshold, we're 12 dB higher. So all of that is telling us that this was a severe shock event. and the effect of that shock on that avionics box needs to be considered accordingly, especially since that avionics box is going to be reflown on an upcoming mission. Okay, here's a different type of shock altogether. This is an SR-19 solid rocket motor, and this is a motor ignition event which immediately sets up what's called a thrust oscillation or resonant burn. And this was a static fire test. So the motor was mounted horizontal to the ground, and it was affixed to a test stand with some big rugged I-beams. So there was no net motion of that motor. It just stayed at the same place. And this was an acceleration time history measured on the forward dome. And let's see, the motor ignition starts off with, if we look at the initial negative peak, almost getting to minus 600 G. So is that going to be severe or not? Well, we're going to find out in a minute. And just to back up a little bit, I think we've talked about these types of thrust oscillations before, but basically the combustion cavity of the motor it's a hollow space, and in some cases it can act like an organ pipe. But anyways, standing pressure waves can set up in that internal cavity geometry as driven by vortex shedding and other effects. And some solid rocket motors have very prominent thrust oscillations, and others don't. And who knows why some do and some don't? I don't know. But here's the tripartite SRS. Q is equal to 10 for the SR-19 motor ignition as measured on the forward dome. So we have the velocity in inches per second and the natural frequency in hertz. And then this peak gets up to about 300 inches per second, which is clearly a severe shock event. So the moral of this story is please do not mount any components on the forward dome of an SR-19 solid rocket motor. But if it is absolutely necessary to do so, then maybe isolators should be used so that the natural frequency of the isolated system is well below 650 hertz. And when I say that, when we isolate components, their natural frequencies might be down, say, 20 to 40 hertz region. Okay, here's a reentry vehicle separation linear shape charge. We've actually looked at this data before when we were doing our SRS analysis, or our SRS webinar for pyrotechnic shock. So here we have peaks getting up to about plus and minus 5,000 G. Again, this was a near-field pyrotechnic shock measured in flight on an unnamed suborbital rocket vehicle. And as we take the tripartite SRS of that particular shock, so we have velocity in inches per second versus natural frequency in hertz. This velocity here is, let's see, we've got 100, 200, 300, 400. This is over 500 inches per second. So clearly a very severe event. So the moral of this story is please do not mount avionics components anywhere near that RV separation plane. But if it becomes absolutely necessary to do so, please use isolators. Okay, we've talked about the El Centro or Imperial Valley earthquake of 1940. The magnitude was 7.1. And it was the first quake for which good strong motion engineering data was measured. And obviously this earthquake was severe enough to cause widespread structural damage, and tragically there were also some fatalities. So we've looked at this data before. This is the acceleration time history for the El Centro earthquake in 1940. And this is the north-south component that was parallel to the ground. And this is the acceleration time history. It only gets up to about 0.3 of a G. So much less acceleration than for, say, the RV separation shock. But of course the duration is different and the frequency content is different between those two types of shock. So if we take a tripartite SRS, Q is equal to 10 for that El Centro earthquake. This is the north-south component. We have velocity in inches per second and natural frequency in hertz. And this is getting up to about 30 inches per second. Now, according to Mill Standard 810E, that's no problem to be at 30 inches per second, but Mill Standard 810E is referring to small equipment like avionics boxes or radios or just kind of small, much smaller systems. But when we evaluate severity for an earthquake, then we're concerned about how a building would respond, and the velocity threshold criteria are different for the case of a building or a nuclear power plant or so on. Here's a half sine pulse. SRS Q is equal to 10, so it's a half sine pulse 10G 11 millisecond, and we're looking at the tripartite SRS. The velocity in inches per second gets up to 25 inches per second, and then we have, of course, natural frequency along the x-axis. Okay, let's summarize what we've taken a look at here, and I'm actually going to add one. So these are the maximum velocities and dynamic ranges of shock events. Now, when I say dynamic range, let me just review. So we take the peak velocity, the maximum velocity along the SRS, and then we also take the minimum SRS velocity. And then we just make a scale factor between those two values. And let's see, the formula would be the delta dB would equal to 20 base 10 log times the ratio of the maximum to minimum SRS velocity values. So that's dynamic range. And here's the maximum pseudo velocity. So I've taken those previous events and ranked them in order. The RV separation with the linear shape charge was 526 inches per second, clearly the worst case event. The SR-19 motor ignition on the forward dome was 295 inches per second. The SRB solid rocket booster water impact, as measured at the forward IEA, was 209 inches per second. Now, here's the one I've added here. If we have a 50G 11 millisecond half sine pulse, which is sort of a case history half sine pulse. I've seen components specified for that test level. That's 125 inches per second. And then dropping down, the El Centro earthquake north-south component was 31 inches per second. The half sine pulse for 10G 11 millisecond was 25 inches per second. And the Vband bolt cutter source shock was 11 inches per second. In terms of an avionics box, of course, we can kind of cross out the earthquake because we cannot discard the earthquake altogether, because let's say we have a launch vehicle and it's on the pad at Vandenberg, California, which is conveniently located near the San Andreas Fault. There's a possibility that an earthquake could occur during the 2 weeks or so that that launch vehicle is on the pad. But in that case, we would be concerned about how the low frequency bending modes would be excited, more than what the avionics responses would be. But otherwise, that V-band bolt cutter source shock was actually fairly benign at the one extreme, and then on the other extreme, that RV separation event was extraordinarily severe. Now, really, to make a more detailed comparison, we also have to know what the natural frequency was of our test article. This is just sort of reducing those SRS plots to a single value, just for convenience, just for rough comparison. But let's say we go back to the SR-19 ignition shock, for example. Well, certainly this 300 inches per second is severe, but if the natural frequency of that component is, say, around 100 hertz or so, then the pseudo velocity would only be around 50 inches per second. Not quite as bad, but just for ranking these events in terms of a single value, we would rank them in terms of the peak pseudo velocity. Now, this is actually Unit 29 that we're on. It's actually going to be a two-part unit. So I'm going to stop the recording here momentarily, just to keep the file size small. And when we come back, we're going to take a cantilever beam and subject it to base excitation. So I'll see you back soon.